Hi Math Dragons, I'm here to teach you about factors. So we've already set up our interactive notebook and we're going to be ready to go. Page 1. So factors. We're going to discuss factor, factor pairs, distinct factors, prime and composite numbers. Okay, here is page 1. This is the page we're going to work on. Here we go. I can identify factors, factor pairs, and distinct factors of prime and composite numbers. We're going to put some vocabulary in here in just a minute, so just set that up for us. And after you set that up, let's copy down this word problem. Charley arranges 18 cupcakes on a party platter. How many arrangements can she create? If you need a little time to write all that, go ahead and pause the video and then resume after you have written down all the work. So I need to come up with a bunch of arrangements for Charley's cupcakes. So I need to see what I can do. Let's see. Let's draw some pictures. Let's create a model. We could do one really long row of cupcakes, right? Okay, so I've got one row of 18 cupcakes. And if that's true, that means I could have had a row the other way, like an array. We're talking about arrays here. Can we come up with other arrangements for the cupcakes? What about two? 2 rows. How many cupcakes would be in each row? I have 2 rows. I could do 2 rows of 9. Well, if I can do 2 rows of 9, can't I do 9 rows of 2? What about 3? I did 1, I did 2. What about 3? I could do 3 rows of 6. If that's true, I could do 6 rows of 3. What about 4? Will 4 work? What about 5? 18 is not a multiple of 5. What about 6? Oh, wait, I already did 6. I wonder if I've come up with all the arrangements. Do we know for sure if I have? Let's take a look at what we do know. I do have one row of 18, right? 1 times 18. Or I have 18 rows of 1, 18 times 1. I did 9 rows of 2, 9 times 2. I did 3 rows of 6, 3 times 6. But then I did 6 rows of 3, 6 times 3. I did 2 rows of 9, 2 times 9. Okay, so all of these arrays, all of these are arrays. They're all arrays. They created a series of factor pairs. Factor pairs are 2 numbers multiplied together to get the next number. So, a factor pair is 2 natural numbers other than 0 that are multiplied together to produce another number. The factor pair is 2, and actually they're 2 natural numbers, which means counting numbers, 1, 2, 3, 4, 5, 6, etc. The factor pair is 2 natural numbers other than 0 that are multiplied together to produce another number. Okay, so if that is true, what are the factor pairs of 18? So factor pairs of 18. They would be 1 and 18, 18 and 1. 2 and 9, 9 and 2. What's the others? 3 and 6, 6 and 3. Those are all the factor pairs of 18. That means 1 and 18, and all those are factors of 18, an individual one. Each number is in a factor pair is a factor of the product. Each number in the pair is a factor of the product. But notice I have a bunch of duplicates. 1 and 18, 18 and 1, 2 and 9, etc. So they keep twinning up. Do I need them to? Let's take a look at this. I really don't need them to, and here's why. I know that something like 3 times 6 is the same as 6 times 3. I know that to be true, because both sides of that equal sign are worth 18. I've proven that. I proved that with my array. Well, what property allows this to happen? This is the commutative property. So if that's true, I don't need to duplicate. It's unnecessary. And when I don't duplicate, there's a special word for that. They are called distinct factors. And there's 2 good ways to get distinct factors. You could either create a list or create a factor rainbow, which you might have done before. So let's take a look at a rainbow for 18. If we do a factor rainbow, we'd start with 1 and go to 18. We test 2, 2 times 9. We test 3, 3 times 6. We test 4, 4 doesn't work. We test 5, 5 doesn't work. And then we're back at 6. This lineup right there, that is called distinct factors. There's no repeats. Now you could do that method, or you could also try a list. So you could either do a rainbow, or you could do a list. So if I do a list, it would look like this. I could do 1 and 18, 2 and 9, 3 and 6, and then you test 4, 5, and you're right back at 6. So you can either go with a rainbow or a list. Now, how does this all deal with prime and composite? Some of these factors are prime and some of them are composite. In this example, what number are we sure is composite? 18. 18 has multiple factors. We just proved it because we did all this work. We drew all these arrays. So, what is a composite number? Composite numbers are numbers that have more than 2 distinct factors. Numbers that have, I'll zoom in for you, more than 2 distinct factors. What is one that we know? We just did one. We did a whole lot of it. We know that 18 is a composite number. 18 is definitely an example of a composite number. Now, Now, some of the factors inside 18, though, may not be composite. Let's look at that. Well, 1 is not prime or composite, so that's not a good example. 18, though, we know is composite. What about 2 and 9? Can anything else go into 2? In fact, nothing else can. Other things can go into 9, so 9 is composite, but 2, the other part, that's not composite, that's prime. So prime is numbers greater than 1 with exactly 2 distinct factors. So what are the distinct factors? 1 and the number itself. So what's an example of a prime number? 2, because the only things that can go into 2 are 1 times 2. Okay, so that is a brief lesson on factors. Important vocabulary surrounded here. You need to know prime number, composite number. You need to know what an array is, a factor pair, a factor, the commutative property, and distinct factors. This is a highly vocabulary-ridden activity here. So you should be all set to do the next example. On the back is workspace. On the back of 1. Let's give you a practice problem to try on your own. Mr. Cecil has 36 chairs to set up in his music room. Mr. Cecil wants to arrange 36 chairs in his music room. How many arrangements can he create? So what you need to do, Mr. Cecil wants to arrange 36 chairs in his music room. How many arrangements can he create? Now, let's look back real quick when we answered this one. How many arrangements can she create? 1, 2, 3, 4, 5, 6. Technically, Charlie can make 6 arrangements. I know that from the factor pairs. So 6 arrangements. But some of those arrangements look the same if I were to turn the platter. So we want to know how many arrangements Mr. Cecil can create. But you're going to need to do arrays. You're going to have to find the factor pairs. But after you find the factor pairs, I also want you to be able to tell me which ones are the distinct factors. I want you to take time to think about that, and on your Google form there'll be some follow-up questions. Good job.